frames of Python code, and it does that by basically extracting graphs of computation, which you then pass to a backend compiler, and it supports basically arbitrary Python. So if there's any Python bytecodes which it doesn't understand, it'll leave them as Python and basically modify that Python bytecode to call into the compiled artifacts. But today, since this is the Triton conference, we're going to talk about the second piece, which is TorchInductor. TorchInductor is a new backend for torch.compile, which converts PyTorch programs into Triton code. And so to motivate a little bit about the design of TorchInductor, I'm going to talk about some of the principles that motivated that design. So the first was we wanted TorchInductor to be PyTorch native. So a lot of PyTorch has a lot of design choices, such as exposed tensor strides, views and mutation, which are different than a lot of other frameworks and hard to represent in some existing compiler paradigms. And so we wanted a compiler which really closely matched the abstractions of PyTorch. Second, we wanted to be Python first. So PyTorch is, it has Python in its name, and we love Python. And looking at sort of the PyTorch community, we see way more community contribution in the Python parts of PyTorch than the C++ parts of PyTorch. And one of the goals of PyTorch 2 was to get more of PyTorch back into Python, because we want it to be hackable. We want it to be easier to understand for our users. And then finally, we wanted TorchInductor to be breadth first. So if you look at a lot of previous compiler efforts and they go really deep on specific things like fused attention, and what we wanted to do is we want something that could support all the weird stuff in Python or in PyTorch, because it's really hard to sort of generalize a compiler if you don't build it into the design. So we put a really early focus on supporting a wide variety of operators. There's three sort of key technologies that helped build TorchInductor. We have a somewhat novel defined by run loop level IR. We also support dynamic shapes and strides using SymPy to reason about shapes and indexing, which is an important feature to preserve in PyTorch. And then we also want to reuse state-of-the-art languages. And so TorchInductor generates Triton code to support GPUs. We support through this NVIDIA, AMD, and Intel, but there's also lots more coming. See the talks earlier today. And then for CPU targets, we generate C++ and OpenMP. So we're generic and we're not specialized entirely to Triton. This is an overview of how the compilation stack works for TorchInductor. We start off with AOT autograd, which decomposes operators. We then have a lowering step where we convert to Inductor's loop level IR. We have a scheduling system which handles fusions. Then we have both backend codegen and wrapper codegen. And the wrapper codegen is basically generating the code which stitches together all the different kernel calls. So I'll run through an example touching on each of these layers of the stack. This is just a simple toy program. It calls x.sine and then y.cosine and then returns both of them. And this is just for illustration purposes. And you can see that we put the torch.compile decorator on it, and I'm using dynamic equals true to enable dynamic shapes. And if you run this with torch compile debug, you can get a lot of the output that I'm going to show here. So the first stage is after decompositions. And so PyTorch has a very large number of operators, in some ways of counting more than 3,000. And so we have a system that basically decomposes and normalizes PyTorch operators into a much smaller set. And so in this example, there hasn't been any decompositions, but if we had something like a softmax here, it would have exploded the softmax into sort of constituent operations. But here we just have now normalized it into what we call A10 ops. A10 is our basically like operator library within PyTorch. This is the defined by run loop level IR. And this is somewhat unique, and it uses Python closures to represent the operations inside the loop body of a kernel. And so here you can see ops.load with a SymPy with a buffer name and then a SymPy expression, and then we call ops.sign to compute the sign op, and then we return the output. And this sort of minimal loop level operator set is only has 54 operators, so it's a very simple way to do code gen, and it's pretty easy to map to Triton and C++. The next phase is scheduling and fusing. Scheduling and fusing is basically when we decide what gets fused with what. There's sort of two key functions in the scheduler. There's can fuse, which basically says, is it legal to fuse two things? And then there's a score fusion, where we basically look at all pairs of legal fusions. We score them, and then we fuse, basically, we have a greedy fusion algorithm where we fuse the highest scores first, and we could continue fusing until we can't fuse anything else. So this is an example of the output Triton that we generate for this program. If you're familiar with Triton, this should be pretty easy to understand. It does a single load, it calls the sine and the cosine, and then it does two stores in the output. And one of the great things about Triton is you can look at the output code of Inductor, and you can understand it. And if you want, you could take this and modify it as well. And then finally, we have the wrapper code that Inductor generates. So the wrapper code does the memory allocations by calling empty strided, and then it also calls the run method on the Triton kernel. And so Triton or TorchInductor is using the ahead of time compilation APIs in Triton to lower overhead. So here's some performance results. These performance results span are speedups over eager mode PyTorch. So 1x here represents going the same speed as eager PyTorch, and we have three different benchmark suites. So we have TorchBench, which represents research models that were highly cited, and it's a really diverse set of benchmarks. We then have Hugging Face, which is mostly transformer models, and then we have TIM, which is primarily vision models. And we can see that TorchInductor is generating speedups of around 2x for inference and around 1.4x for training. And it's outperforming a lot of other different compiler technologies out there. This is an ablation study where we basically want to try to figure out, okay, where are the Inductor speedups coming from? And what we've done is we've taken just Hugging Face, so just the middle graph in the previous slide, and we've computed the geomean speedups across these 45 models and we've one by one removed different optimizations from Inductor to try to figure out sort of which optimizations are contributing to the speedup. And basically the hypothesis here is that if removing an optimization causes a big slowdown, then that optimization is more important to the performance of Inductor. So you can see that there's lots of optimizations here. I'm not going to talk about them all. One interesting one is the matmul templates line, the sort of third line here. And so for most operators, Inductor generates Triton code entirely from sort of first principles using basic IR. But for matrix multiply specifically, we have handwritten templates, and we can fuse epilogues onto those templates. And for some models, we see pretty big speedups from these matmul templates. But across this entire benchmark suite of 45 models, we can see that the effect of actually just completely turning off templates and only using first principles code gen is pretty small. And the fact that we're primarily getting our speedups from fusion opportunities. And specifically, the fusions are represented by fusions and inlining. So there's basically two different ways that we combine PyTorch operations into a smaller number of Triton kernels. One is inlining, where we basically duplicate something to all of its consumers. The other is fusing, where we basically combine two kernels in the scheduler. And you can see that if I disable both of these, TorchInductor actually goes significantly slower than eager mode PyTorch. This is this last line. And the reason for that is by decomposing operators in PyTorch, we're actually introducing slowdowns where the decompositions we do in lowering, Inductor needs to fuse stuff to actually get back to 1x there. And so we're seeing a lot of speedups primarily from this fusion. And with that, I'll hand it off to Horace.
Thank you. Given that we're at the Triton conference, I thought people might appreciate kind of a little bit of a deeper dive into kind of what exactly is TorchInductor doing with Triton IR and what kind of things we're able to do and leverage Triton for when generating code. So if you guys remember, kind of maybe 2 years ago at this point, one of the original posts, or like one of the original examples in the Triton original blog post was about generating softmax from scratch and kind of showing that it outperforms PyTorch. So here, we took the same example, the same previous code from the blog post, and kind of passed it through Torch compile to see what the Triton code that we emitted looks like. And you can see that this code looks very similar to what you might write from scratch when kind of writing PyTorch softmax, maybe with a little bit less informative variable names than a user might use. But kind of in principle, the code looks very similar. You have the load, broadcast, where, and things like that. And one thing you can also note here is that this code does support dynamic shapes. In particular, in this particular case, we've chosen to keep the batch dimension dynamic while keeping the reduction dim static. And so this is kind of a cool example of showing that and this is kind of partially the goal of TorchInductor, is to kind of eliminate a lot of these relatively simple kernels and kind of be able to do them reliably and emit code that's efficient. So unsurprisingly, if you kind of benchmark this on a variety of different shapes, the results between the Inductor code and the Triton code look very similar, and they both kind of outperform the PyTorch code. And this is kind of mainly because in this case we were generating a persistent reduction where you kind of load the row once and keep it in shared memory when doing your operations, as opposed to reloading your kernel multiple times. And so perhaps you might ask if PyTorch is kind of only generating it's generating kernels that you can kind of write by hand. What are the kind of additional reasons to kind of use Torch compile to generate your code? And so one of them, for example, is as your reduction dimension increases, at some point you can no longer fit every single row in memory. And so, for example, this was a common limitation that I think people practically ran into when they tried copy pasting the Triton softmax kernel to try and for different shapes. Is that at some point, it started to overflow and kind of use too much registers and shared memory. And so, one thing that PyTorch kind of Torch compile can do by kind of having control of the compilation process is that we can make decisions around, should this reduction be generated in a persistent manner or in a non-persistent manner. And so it kind of automatically makes that decision based off of things like register pressure, based off of things like, how large is your reduction dim, and things like that. And so you can see here, there's a loop here to kind of, do the a kind of a blocked reduction in a loop that's kind of non-persistent. And so kind of, as Jason mentioned, the way we do codegen is very generic. And, we have not done any specific pattern matching or kind of specifically optimize a softmax kernel. And so you can imagine there are many variants on softmax, which I think people are perhaps underappreciate sometimes about the kind of complexity that even kind of, a basic softmax will give you. And so you can take examples like this where, maybe you have two softmaxes in a row, or you have an output of a softmax that is then, passed into another kernel, and then you need to output both outputs. Or maybe you have two softmaxes together and then they combine together in a single kernel. And so if you try compiling each of these with TorchInductor, each one of these gets loaded into a single Triton kernel kind of from scratch due to kind of our generic first principle fusion. So as Jason mentioned, although we can generate many kernels from scratch, and in some sense we are kind of tackling the relatively easier codegen problems, things like matmuls are obviously very crucial for deep learning performance. And our general kind of philosophy here is that generating matmuls is really hard. And even with something like Triton, there's all sorts of tricks like L2 swizzling or rematerializing registers or stuff like that in order to kind of get the peak performance on your matmuls. So instead of trying to attempt to kind of codegen these from scratch, use on things like additional things onto the end. So in this case, we take the output of the matmul and we fuse both a broadcasted add in the terms of the bias, as well as a cosine operations, and then we return all three of these values together. And this is kind of flexible codegen system. It allows us to kind of do arbitrary amounts of stores and things like that. And so if you take a look at kind of a sample of this generated code, you can see above there you have very much the handwritten template code for Inductor for matmuls. But at the bottom here, we have an automatically generated suffix that both does an extra load, reading in an extra input, as well as writing two extra outputs. And so this can kind of all be done automatically with kind of Triton templates that are passed in. Or sorry, Triton templates that like we add to the compiler. Another kind of example of a kernel we can generate that's I think kind of really takes advantage of Triton's level of abstraction are things called like for each kernels. You can kind of often see them in like fused optimizers. And in this case, like what you have is you have like a simple pool-length operation across a large number of small tensors. And so this kind of is like a common issue you run into if you just kind of omit naive code gen for each one of these operations, because each kernel only launches a small number of blocks, and it's difficult to get a large amount of occupancy on your GPUs. So one common strategy here is you launch a single kernel that kind of does different things for each block. And so this, you can see here, like we emit code that branches on which block is being, like which thread block you're currently on. And I think this is a type of kernel that's like kind of really takes advantage of Triton's abstraction level, which is kind of at the blocks, as opposed to kind of a higher level, just like generic loops over your code. And so see here in this case, we have we kind of fuse like an arbitrary like for each add, for each mole. And so this kind of allows us to both perform vertical and horizontal fusion of optimizers from scratch. And kind of, I want to kind of mention another kind of cool thing that we can kind of do, take advantage of kind of the tight integration between PyTorch and TorchInductor. So for example, one thing that kind of people often run into is you have things like attention operators, like flash attention, where you want to make a pretty trivial modification to the core of the kernel. So I mean, for mabbles, it's like epilogues, but for attention, you might want to add like a relative position bias or things like this. And today, oftentimes, what people are kind of forced to do is people are forced to kind of drop down into the Triton code, or I mean, Triton is even way better than dropping down into the Cullis code and trying to modify it. But even so, you have to drop down to the Triton code, refactor it, kind of get it to work, and then write your own backwards formula, and then kind of integrate it together in order to work. But by taking advantage of Triton templates and kind of the PyTorch kind of general lowering system and autogram and stuff like that, we can kind of provide APIs like this that kind of allow you to like kind of parameterize these kind of more complicated kernels with trivial modifications. And this kind of like more work in progress work that we kind of hope to leverage. And the final thing I kind of want to touch upon is like, I think one thing like that Jason mentioned is that really TorchInductor, you can really view it as like a PyTorch to Triton converter. So for example, if you take models like Resin 18 and you lower it into Inductor and you take like the output code, what you see is 30 different Triton kernels that have been generated, covering everything from like batch norms to relus to batch norms plus relus, or all kinds of fusion like this. And the only kind of non-Triton kernel is like atypical convolution. Similarly, if you try to compile like llama decode like text generation, we're kind of left with like 2 kernels like top K and scale dot product attention, and 23 other Triton kernels that have been generated. And this is kind of partially why you can, if you, from like the previous presentations, you can kind of take this code and reuse a lot of it in order to target other hardwares and reuse a lot of the optimizations that TorchInductor is doing, including things like the matmul templates, the softmax fusions, and things like this. Yeah, so thanks for, that's all we have. Thanks for listening to the talk. We'll also have another PyTorch conference on October 16th, about a month from now, that we'll be talking a bit more about kind of other work we've kind of been doing with Triton and TorchInductor. And you can find the code here, and we're also hiring an email that address if interested. Thank you.
How do you, can you hear me okay? Okay.
Yeah.
How do you generate nested loops?
What do you mean by nested loops? Like
So for example, here, I think most of the case you have a single for loop in a Triton kernel.
Yeah.
Is there any case you can generate nested loops in Triton?
So what we'll do is we'll end up taking multiple loops and we'll flatten them to a single loop. And you can also encode a lot of the, it's often better to encode loops as bigger blocks. So like if like rather than like putting a loop in the, if you're doing something pointwise, rather than putting a loop in the Triton kernel, it's better just like basically like run more blocks, basically encode it in the, encode the loop in the block. If you're doing a reduction, we basically will flatten the reduction. Basically, if you're reducing on multiple dimensions, we'll just flatten it into a single loop. And so basically it'll end up as indexing math. So there'll be a modulo in your load rather than doing multiple loops.
Gotcha. That's smart. But do you see any value in having a like sort or top K kernel written by Triton?
So I think until really recently, and maybe still so, it's pretty hard to implement a sort in Triton. I guess maybe Phil, is sort coming soon, or?
I think eventually we do want to have sorting. I think top K maybe more than sorting. So maybe full sort's not coming anytime soon, but I think for top K it's something we've started looking into. We just haven't really had the staffing to take a very deep dive into it, but it's something we're interested in. Yeah. You can already do top K if K is small by like iterating argmax, which is how I've been doing some of them. But yeah, for like large K, at the end of sampling forward pass, it's harder. But yeah, we're working on it.
Like in general, like the kind of more Triton has expanded, kind of the broader of a scope, and the more kernels we can kind of turn into Triton. For example, someone, it might be Thomas, I think recently added scan, and so that kind of further expands the scope of like what we can lower from Triton into Inductor and kind of do additional fusions and things like that.
I had a couple of questions about dynamic shapes. So one of the reasons for doing dynamic shapes is to reduce build time, so you don't have to do the same graph with multiple different shapes. So how do you achieve that in the sense that when you execute in PyTorch, you get a specific shape rather than a dynamic shape? And when you're running in dynamic shape mode, you generalize some dimensions, and then later, how do you reuse that code for similar but different shape?
So the general kind of dynamic shape system is kind of you like in your first compilation, you kind of like some amount of shapes will be symbolic and you trace through. And as you kind of trace through, you will accumulate some number of like guards or like preconditions for this compiled graph to work for those shapes. So for example, one guard might be that this value has to not be 1. It has to kind of be more than 1. But you can also imagine kind of other types of guards depending on what's in the user code. Or other kinds of like conditions like that. Okay. There's definitely like a lot of interesting work in dynamic shapes, and we haven't kind of fully explored the space. So for example, today I think we only generate one kind of kernel for like across the entire dynamic shapes space. But you can imagine that we might want to be able to change the like like in this case, for example, the batch size is dynamic, and that case is relatively simple to do, and the performance numbers were presented with a dynamic batch size. Okay. But if your reduction size is dynamic, you're now maybe confronted with like needing to generate multiple different kernels to cover different parts of your shape.
And how do you do dynamic checking? For example, let's say I have some dynamic shape compiled program, and then I later give it the wrong shapes, right? Try to run it.
So the general kind of system is like all the shape checking is kind of lifted to the beginning of the graph. Mm-hmm. Like the most kind of common case is that your dynamic shapes are coming from the input. And like all the shapes in your program can be expressed in terms of the input dynamic shapes. And so in that case, like we have the set of preconditions that we check on the graph for your dynamic shapes in order to see whether this graph is valid.
Okay, yeah. Great, thanks.
Yeah. And because we're a just-in-time compiler, like one thing we can do is like we can like dynamically recompile.
You can fall back to static.
Yeah, or we can fall back to eager mode too.
Okay. Yeah. Do you have any performance data on how the build time is reduced by your dynamic shapes?
I mean, it's kind of very much dependent on the like. Workload where your shape changes very much, very often, then obviously it'll reduce compilation time by quite a margin.
Okay, great, thanks.
Okay.
All right, thank you. We are running a bit low on time, but we have a couple online questions we wanted to get to. So the first one is, does the kernel matmul kernel and other vector processing kernels work well in TorchInductor?
Yeah, so currently matmuls are templates, as we said, and we can append an arg to that template. The restrictions are, so the epilogue can contain, point-wise loads and stores. It can do scatter operations, so you can do like indirect writes. We don't currently use reductions onto matmuls, but basically anything Inductor can generate code for that doesn't require reduction. It can append onto any template, including the mapmul template.
And the second question, is there any optimization or transformation that helps Inductor to generate kernels that are CUDA capturable? For example, for token generation, we have increasing prior KV cache length for attention.
Like CUDA graphable, or is that the question? Like to generate code that's CUDA graphable, or CUDA? I missed that part.
I'm not familiar with the concept. It says CUDA capturable. Maybe it means there's a kernel written in CUDA for it.
I think if it's CUDA graph capturable, we don't currently do like any of these kinds of optimizations today. For example, if you have like a non-zero, we'll like incur a CUDA synchronization. You can imagine in the future we can make kernels that can avoid this, but that's something we've thought about, but not something we've done today.
Yeah, and currently what we do is we have a static analysis pass to say, can we apply CUDA graphs? And if we can, we'll automatically apply it. And if it's unsafe to do so, if you have like a synchronization in your program or like a hosted device copy or something like that, we'll automatically disable, we'll sort of transparently disable CUDA graphs.
For transformer inference, like there are ways of kind of writing your KV cache to kind of have it be CUDA graphable. I'd encourage you to come to the PyTorch conference to hear more in a month.
Yeah, we are out of time, but thanks, Jason and Horace. So the next is another video talk. It's by Sharad from Google. He'll be speaking about the Palace Ajax kernel language.